Can you hear me? Thank you. And because the talk is relatively short, I really cannot go too much into detail, and there will be some assumption about what you already know, especially about AFM. So the motivation with this new technology called AM/FM is that a lot of people in the AFM world want to do mechanical measurements with their AFM. It's a big trend in all kind of areas. So, so of course, that's very exciting. And there's a lot of things are happening these days in the field, and you will see a lot of paper published, and a lot of manufacturers trying to help everybody in this area. Unfortunately, it is not that simple. It is not that easy, and a lot of people are trying to hide things underneath the rug to make it look easy and simple. And I wish I could say that, but it's not. So let's see a little bit what we have been doing lately at Asylum. And I'm going to restrain this talk to really how these days we're going to try to measure stiffness and loss tangents on some sample using AM/FM technology. Knowing that AM/FM technology allows to do some other kind of measurements, but today I'm only going to talk about stiffness and loss tangent, which assume already that you guys know enough about AFM, know enough about tapping mode, and thank you, Scott, for giving this great presentation already, explaining to you what it is if you are not using it. And that's assume also that you guys know what a loss tangent is on material science, because I don't have time to, of course, explain all of that. But again, I want to emphasize on the fact that there are a lot of things underneath the rug that people may not tell you in the field of nanomechanical measurements. But we are trying to, make things accessible in a way that makes sense at the same time. As far as loss tangents, as people who do material science know, it's about energy loss and storage energy, and these two measurements are linked together, like nurture and nature in your personality, or measuring the area of a rectangle, the length and the width work together for the end result. And that's what we are trying to do with the FM, where we want to measure the loss tangents, and for that we're going to use phase mode and amplitude measurements, and I'm going to explain to you how we do that. And we use also this AM/FM technique to do stiffness measurements. And again, this is using tapping mode, and dual AC is really the core of this technology. When you want to do some stiffness measurement with, in a dynamic way, again, what people do in material science, you apply some oscillatory stress to a material, and you measure the strain. And the storage modulus will be the in-phase elastic components of the material, and the loss modulus will be the out-of-phase components of the strain, which is really the viscous component. And the loss tangent, by definition, is really the ratio of the loss modulus to the storage modulus. So all of that is really pure definition. The reality is that most materials in this world are in between. None of them are, well, let's say that most of them are in between being, most of them have some viscoelastic behavior between elastic and viscous components. And the goal here is to really try to measure these two modulus. So how do you do that with an AFM? If you recall what Scott just told you, when you do tapping mode or AC mode, what you do is you oscillate the probe of your AFM, you look at the resonant frequency, and at the same time, when you're on top of the peak here, which is the highest response of the cantilever, when it resonates at its resonant frequency, you look at the phase signal. The phase signal, as Scott explained, is a difference, actually. This is a very confusing term, but this is the difference. It's the phase shift between the driving signal that is applied to the cantilever and the response of the cantilever. And this phase, difference in phase, the phase shift here is along the black curve. If there is some interaction, and there are interaction between the tip and the sample, this interaction can be repulsive or attractive, as Scott described, and you will have a phase shift. If you are in a mode where you have a repulsive interaction, the phase goes down, so you have a decrease in the phase shift. And if you are in an attractive mode, you have an increase in the phase shift. So this is the basic AFM mode where you do tapping mode. What we do with dual AC gets a little bit more complicated. So this is really what we do in practice, where we oscillate a piezo, we look at the response of the cantilever, and we measure the difference between the driving signal and the response, and from there we get the topography. So I'm going to go a little bit further. When we do dual AC, what we do is not only we oscillate a cantilever at the first resonance. So let's say in that case, this is a typical cantilever we use in air. The first resonance is at about 80 kilohertz. And then, but what we do on top of that, we apply a second voltage at a different frequency. And we use a second mode. So now we oscillate the cantilever at 2 frequencies. And the key here, I'm sorry, I don't want to do that. The key is really that the signal of the cantilever, the response of the cantilever now has this kind of motion here. And you want to do it so that the second amplitude of the cantilever corresponding to the second mode is very small compared to the first mode. So that looks a little bit messy in practice, but really what you have is on the first mode of your of the peak, you are going to look at the amplitude. You're going to use that to get your amplitude image, your topography. And we're going to see that on the phase of the first mode, that's this signal that we're going to use to measure the loss tangent on the material. And on the second mode, we actually apply a feedback. And the feedback is in the change of the frequency of the cantilever. And I'm going to go back to that a little bit more into detail later. And you apply a feedback on the phase of the second mode, and you look at the difference in the shift in the frequency. And that's the shift in the frequency that gives you the elasticity. And I'm going to explain that a little bit more into detail later. And I'm going not to talk about dissipation right now, because I want to stay as simple as possible. But remember that you do dual AC on the first mode. That's how you're going to get the topography of the sample and the loss tangent. And on the second mode, you're going to get the elasticity measurement. So let's go a little bit more into details now about the loss tangent. I'm going too fast here. So again, you have your first mode, and this is at that point just regular tapping mode where you have a feedback on the amplitude of the oscillation of the cantilever. And you're going to get, of course, your typical AFM data, topography, and the loss tangent. How does that work? I'm going to try to make it very simple as far as the mathematics here. But as you may know, the loss energy is the dissipative energy is the inelastic energy. And in the AFM world, we have been able to relate that to this equation here shows you that it's related to the sign of the phase. And also, it takes into account the ratio of the amplitude of the oscillation versus the free amplitude of the oscillation. So it's getting a little bit complicated if you guys don't do AFM. However, as soon as you start doing AFM, this is relatively simple. When you do tapping mode with an AFM, you have a free amplitude of the oscillation before the tip is engaged on the surface. And that's the amplitude of the oscillation when the tip is engaged on the surface. So here with this simple equation, you have access to the loss energy. And the storage energy here is directly proportional to the cosine of the phase. And if you do the ratio, which is very simple, you get the loss tangent of your material. It's pretty simplified, but it's not an ugly math here. It's actually pretty simple at the end. You have a pretty simple equation. Now, what is very important here to remember is not the equation by itself. It's the fact that if you look at this equation here, all you can see is this is the amplitude of the oscillation. This is related to the phase signal. There is nothing in this data that is related to the chip shape. And it's very important to remember that, because as we're going to talk a little bit further, a lot of the measurements with the AFM depend on the chip shape. Now, with this technique here, it doesn't matter what your tip will look, you can have access to the loss tangent. Here's some data. I can show you. I need to check the time. So in this image, we used an elastomer, a blend between a polypropylene and some soft rubber. I don't remember what it is. And you have the topography, you have the phase signal, and this is your loss tangent. And coming from the previous slide, you can see that this is pure calculation from the phase signal coming from the first resonance of the cantilever. So the beauty is that it's very fast to make this type of measurements, and it's not dependent on the shape of the tip. So very simple at the end. And now that this kind of feature is included in your software, you get that instantaneously. You do AC mud, and you get the loss tangent of your material. That's just some measurements we have done, and this is comparing also the data you can obtain with this kind of reference method that people use in material science, the DMA technology. That's another example here where this time we have a ternary blend of polypropylene, polystyrene, and polyethylene. And again, this is the loss tangent that you can measure with the DMA method here. And this is the result we can get with the AFM. I think I'm missing something here. And you can measure this ratio of the dissipated and lost energy and compare that with DMM. And of course, as with any AFM technique, you can display that on your image at the same time as your topography, and you can overlap this data. I played also with all kind of materials, and I took some coffee bag, actually, and just cut it, make a cross-section, you cryotome that, and then you do your regular AFM technique. This is the topography of this coffee bag, a cross-section. This is a phase image. And if we go a little bit more into detail, you can measure the loss tangent on the different material. Now, I don't have the exact composition of this material, so I'm kind of guessing what they are. But in any case, you have, like, for example, this aluminum material here compared to what they call the tie layer, which is really kind of a sticky layer to put together other materials. This is some kind of polyolefin materials. I'm not a polymer science, so I have no clue about what I'm talking about. But in any case, you can see that you can easily differentiate the different type of layers with the FM and measure the loss tangent, and that totally correlates with the topography and the different materials that you are studying. So loss tangent at the end can look pretty simple. You do just regular tapping mud, and in the software right now, you just click on opening this channel loss tangent, and you get your data. Not necessarily easy to understand what it is, but the fact is to do it, it's pretty simple. If you want to use AM/FM and measure the elasticity, it's a little bit more complicated to understand, and I'm going to try to make it look simple, but I don't want to put things underneath the rug at the same time. So elasticity measurements in the FM world all start with the Hertzian model, where this guy in the 19th century was studying the compression of lenses. And we still apply these models in contact mechanics. And if this is just a representation of the model in a kind of simplified way, but what is important to remember is if you push on the sample with an AFM tip and you assume that your tip is a sphere, you can come up with this equation that tells you, I don't know why it's moving here, that the stiffness of your sample is proportional to the elastic modulus of your sample and to the contact area. In other words, the contact area, and the contact area depends on the load of your tip and the radius of your tip. So now what we are interested in measuring is really this number here, the elastic modulus, the stiffness of your sample. And you can see right away that this value here, this intrinsic property of your material, depends on this value, which is the contact area. Unfortunately, this contact area will change over time, depending on the tip. Well, I would say first it depends on the initial shape of the tip, which you don't know. You have no access at that level to know the contact area, the shape of the tip. And this is changing over time. There's been a lot of publication over the years that show that the contact area between your sample and your tip change over time, and we don't have access to that value. And you can see that in this equation, this is a square value. So it's very important and will have a big effect on the end result of the measurements. So, people have been taking tons of pictures of tip with electron microscopy, and you can see that it's very, very difficult to control the shape of the tip at the end. And not only it's difficult to know what it is exactly at the end result, but this is going to change over time. As you are scanning your sample, the shape will change. And that kind of issue, a lot of people will not talk too much, and that's part of what people put underneath the rug when you do these measurements. They will not tell you how they take that into account in the equation, even though this is a big part of the problem. So what we are doing at Asylum right now is we look at the second, again, we go back to this second mode of the oscillation. And we have a feedback on the phase of the second mode. And depending on the interaction between the tip and the sample, which means depending on the mechanical property of the sample, you will have a frequency shift of this second mode. And we are looking at this frequency shift. It's kind of intuitive to think that if the tip is tapping on something very hard or on something very soft, the frequency shift will be different. That's kind of intuitive, and that's what it tells you here, that the shift in the resonant frequency depends on the stiffness of your sample here. It's actually, to be honest, the stiffness corresponding to the tip-sample interaction. So we start from here. Again, the shift in the resonant frequency of the second mode depends on the stiffness of the sample. And we know that this stiffness is also proportional to the contact area and what you want to measure, which is the modulus, the elastic modulus of your sample. From there, we get the elastic modulus, which is again proportional to this frequency shift, but you can see that in this equation, you still have the stiffness of your sample, the contact area, and of course the second mode frequency, but that you know it. So what are you going to do with that? What we do some kind of NSAS, which is an educated guess. And we can think that between two materials, if you do not change any parameters, you use the same tip with the same parameters, you can guess that your elastic modulus will be only proportional to a calibration factor and your shift in the resonant frequency. And that's what we are doing right now. So we do dual AC. We have the second mode with a feedback on the phase. We look at the shift in the resonant frequency of the second mode. And we're going to calibrate first the shift of the frequency using a reference sample. And we're going to enter this parameter in the software. This is the calibration factor. And now you can use this calibration factor on your sample. And you're going to measure the shift in the resonant frequency, and that will give you access to the elastic modulus of your sample. So this is working pretty well. That's what we again do here, where we apply a second, the second mode of the oscillating. So we apply a second oscillating signal to the cantilever, and we look at the phase and we look at the amplitude. We apply a signal, a feedback on the phase of the second mode, and from there we can calculate the elasticity. And what we do is, again, we use, so that if I don't want, if I just, I can just not calibrate my system, that would just be fine. In this case, what I did is I use, again, this ternary blend of polymers that have 3 different values of elasticity, and I can see a big contrast between the different area. The numbers, I cannot measure any numbers at that point. I can just look at the shift in the of the resonant frequency and make a difference here. And that's also what I did here, where I cryotomed this elastomer. What I did is I glued together a rubber and a latex sample with some epoxy, cryotomed that, and then I can do some loss tangent measurement and some stiffness measurements. At that point, this is not calibrated. I just can make a very nice comparison between this type of material. Visually, you cannot really see the difference, but if you plot that in I've lost my words here. Anyway, you can see here 2 peaks in the shift in the frequency. You can make a nice difference between the latex and the rubber. I cannot quantify that here right now because it's not calibrated. But however, and you can also get pretty high resolution. This is actually a few nanometers resolution. You can see the lamella inside your polymer at that level. And what I wanted to show is here, what we do is we use a reference material. We use a polymer from NIST. We know what the elasticity or stiffness of this sample is. And from there, we know what the shift in the resonant frequency here is, and then I can use that calibration factor on my other sample, and now I can quantify my results. This is still in the units are still in the shift in frequency, but it works. So here I can just, again, assume this very simple equation, knowing that the elastic modulus is proportional to the shift in the frequency here. And here, this is the end result, where now I have values in gigapascals here, because I was able to calibrate. So at the end, there are a few things that are keys in really these measurements. Is first, you really need to be in repulsive mode. As you remember in the previous talk, you can now in AC mode know when you are in repulsive or attractive mode. It's very important that you are in repulsive mode and you are tracking the surface really well. And it's very important to carefully tune your cantilevers at the first and second mode. You can do it on other modes other way. You don't have to, by the way, you don't have to be in first and second mode. You can do that with third mode and so on. But you have to really be at the peak of the resonance and really make sure that your phase is at 90 degrees very precisely. And then if you are doing that, you will be able to not be too afraid of not ignoring some of the issue with these measurements. And I think the big message in these measurements, it's really that the tip shape we can circumvent the problem of the tip shape because it is a big issue in this measurement, and a lot of people try to ignore it. But the fact it's a reality, the tip shape will be important in these measurements, and we need to be able to make some reliable measurement despite the fact that we don't know what the shape of the tip is. Thank you.